behavior, typically near those flat regions in oscillated material, and they can form one, can form many. They also have interesting behaviors in that they can be out of phase with each other or in phase, and two oscillons that are in phase tend to repel each other, two oscillons that are out of phase attract, so it acts like a charge effectively. In terms of the way the oscillons move around and couple, and I've seen pictures where you have chains of oscillons up and down, forming like a chain or a loop. And a lot of interesting patterns. Some people theorize that these are the fundamental behavior, typically near those flat regions in oscillated material, and they can form one, can form many. They also have interesting behaviors in that they can be out of phase with each other or in phase, and two oscillons that are in phase tend to repel each other, two oscillons that are out of phase attract, so it acts like a charge effectively. In terms of the way the oscillons move around and couple, and I've seen pictures where you have chains of oscillons up and down, forming like a chain or a loop. And a lot of interesting patterns. Some people theorize that these are the fundamental excitations that make up all of these patterns. When I was at Northwestern, I worked with the guy who discovered these, Paul Oppenhauer, and he didn't think that was the case at all. So it's still a question about some active interest. Okay, shearing forces. Say I take a bunch of grains, put them in a confined space, put a little pressure on them, and then apply a shear. That's the stuff that I'm studying in particular. This is work from my PhD thesis, simulations, where we had particles in a box, and we did a trick where the particle rolls off this end in a simulation, you just pop it back in this end, so it's effectively an infinite tube. And what we do is we start to apply some force and look at when the bed started to flow and how it responded. The response is bistable and history dependent here. So when I apply some shearing force F sigma, various things happen. We fluidize. And in particular, what's interesting is that I start out from a state of no flow, and I start to increase the shear slowly. It stays static until it reaches some transition shear, which varies as a function of configuration. And then it suddenly starts to move, hops up fairly quickly to this characteristic curve. If I decrease it, it follows this curve smoothly down to some other point here. So the direction I move around this graph makes a difference. And what that tells me is that at an applied shear of, say, 0.3, and this is the ratio of the applied shear to the pressure that's applied, hold the plate down, at about 0.3, I can't tell if someone tells me, okay, I've got a fluid, I've got a granular system, and I'm applying 0.3 shear to it with this model. I can't tell whether it's moving or still from that shear. If it was still, it will remain still. If it some other point here. So the direction I move around this graph makes a difference. And what that tells me is that at an applied shear of, say, 0.3, and this is the ratio of the applied shear to the pressure that's applied, hold the plate down, at about 0.3, I can't tell if someone tells me, okay, I've got a fluid, I've got a granular system, and I'm applying 0.3 shear to it with this model. I can't tell whether it's moving or still from that shear. If it was still, it will remain still. If it was moving, it will remain moving. If I increase it or decrease it, it'll move along this curve or move along that curve, depending upon its history. So this is what the bistability. In this regime, there's two different stable behaviors. Up here, only still is stable. Up here, only moving is stable. But in this regime in the middle, either still or moving can be a stable configuration. That's why avalanches are a problem. You know, the snow pile on a hillside is in some static state, and it's still, and until it gets perturbed to the point where it reaches this critical stress, and once it reaches that stress, it very quickly starts to flow with a fair amount of energy. And that's what happens in an avalanche. You go from this state, something perturbs it, and suddenly you move into this state, and you get flow, and then all the snow around it that is near critical state is also kicked into flow, so a huge release of energy happens. So understanding this behavior is important to understanding avalanche dynamics, earthquake dynamics, and various other behaviors that these things model. Okay, having obtained the results of simulation, the work that I'm doing with Will is to try and figure out what happens in an experiment. We can't create an infinitely long tube where we teleport things from the back end to the front end in a real experiment, so we're going to use a drum flow. We're going to use a slope surface to apply the shear instead of a weight and a direct direct forces on it. So we're doing a drum rotation and shaking experiment. It looks like this. This is the model we put together. We're partly done building it already. Today we're going to put these parts on, hopefully. And this shaker here shakes the cylinder up and down. It's restrained by these 3 rods to move in one plane. And those support structures. We're going to have a motor over here that I haven't put on yet, that's going on the illustration, that's going to turn the cylinder as well. So we can do both shaking and vibration simultaneously. And this experiment hasn't been done yet, and I'm interested to see what kind of results we get from it. We'll track the surface by using a laser at an angle. So shining a laser down at some angle, making a line, not a point. And then as that line shifts, as the surface rotates, that line will shift, and we can monitor it with the camera, figure out what the surface is doing, monitor the angle that the surface is at. And our goal was to do this with lots of different materials, lots of different vibrational energies, rotational speeds, and get a sense of what's happening in the system. I want you to run and vary lots of things, work with dry and damp systems, different grains, different size grains, different shapes grains, different roughness grains. A lot of things we can do with it. It's a very versatile experiment. I'm very excited about the possibilities that it presents. Okay. I want to thank Will for wanting to work with me. The first time committing an effort in this. I want to thank the Eureka program for sponsoring the research and Dr. Konzakli for running this excellent program. I don't know if you guys appreciate how much benefit you're getting to your careers and your education from this program, but working with people one-on-one and doing stuff is really great. It's a phenomenal opportunity. You should savor this and, build on it as you go forward in your academic and then professional careers. And finally, I want to thank all of you for your attention and time today. I hope this presentation has introduced you to some of the interesting and unusual behaviors of granular materials, and answer some questions you may have had, and maybe giving you some more. So, any questions? Before I take questions, I have one other thing I want to show you. This is the last demonstration I brought. This is a simple bottle. This is an old dish soap bottle with a layer of sand and water in it. You open the top so it's free to room. So I'm going to change it. And normally, what would happen if I squeeze this bottom? You'd expect the level of the water to go up, right? Well, what's going to happen here is that the grains have formed an efficient configuration on the bottom so that the grains can be as low as possible, pulled by gravity because they're denser than the water, and the water flows on top. If I squeeze the bottle, I'm going to disrupt that efficient configuration and produce gaps and voids in the sand in the bottom, which the water will then flow into. So as I squeeze, you see that layer of water at the top? It's much thinner now. It's up there. It's gone. So now I've got no water at all on the top. And as I let this sit, it'll eventually rematerialize as the grains recompact themselves. So have you ever walked on the beach right at the edge of the water where it's sort of the waves are lapping up and it's wet sand, but not underwater, but just dampened periodically? And someone walks on those, you can see their footprints for a while. That's the effect that's happening. They've disrupted the structure of the sand underneath, and that sand is more porous and absorbing more water, so the footprints you see are actually dry patches. Their weight has done that. So I'll pass this around. You can play with it for yourself. It takes about a minute for the water to come back, and maybe a couple squeezes to get it all drained. And I try not to spill it.
Will the sand go back to the beach?
It eventually settles down into a more efficient configuration. Probably not the original one, but something similar, where more of the sand is down lower and the water is pushed upward because it's lighter. Any questions?
How controlled is your testing apparatus to moisture or dryness of the air?
Yeah, that's the humidity. Well, the apparatus itself is sealed. So, and we have a desiccator so we can dry off the samples if we need to. But the basic plan is to set it, it's pretty dry here, the humidity is low, so we don't have to worry too much about that. Close it up, leave it closed, and not worry about it too much, is the basic plan. Going forward, we may do some experiments where we add water on purpose and get the damper structure, but once it's in there, we seal it up and it's closed. We're not having an open flow system. So humidity control is pretty good in that sense. We can't explicitly extract it out. I mean, if we need to, you know, if we work with Houston, for example, we probably need to have some method of drying it out. Put some sort of getter in there and leave it sitting for a while, and pull the getter out, close it up, and seal it and leave it. But I don't think it's going to be much of an issue. We have some control over it. If it turns out that we're seeing humidity effects, then we will do something about it. Further, a little bit of humidity can be a good thing because it reduces static electricity effects a lot. Really dry material, you then get static effects where particles would stick and get stuck in sidewalls and there's other things happening. So, yes?
You said the grains were like a powder, on the powder side, there'll be static forces.
Yeah, static forces become much more important when the size gets smaller.
Okay. But how do they get reduced, or how do they get like ignored when it's on the grain size?
I'm sorry?
Like how the static forces disappear when it's granular?
Well, when it gets bigger, static forces are still there, but the forces are much smaller relative to the weight of the material. So typically the charges on the material are a function of surface interactions, things rub against each other and their surfaces are in contact. And the mass of the object is a function of the volume. So as you increase the size of the particle, the volume to mass ratio goes up, and the importance of static effects goes down. It's the difference between, say, regular sugar and confectioner's sugar. Confectioner's sugar is like 10 to 100 times finer than regular sugar, and it's really a powder. It's like a dust, and you dip a spoon in it, it kind of sticks.
Right.
Whereas regular sugar, you dip a spoon in and pull it out, and all the grains fall off. So that's one example to sort of think about where static electricity becomes less important. I also have hay fever, and the pollens that I'm allergic to are really small, much smaller than a micron. So traditional filters that just have like a cloth mesh that catch, but don't really do anything for pollen. So I use an electrostatic filter in my bedroom where it just creates a huge electric field, the pollens get charged. And the nice thing about an electrostatic filter is that the smaller the particle, the stronger the filtration is. The opposite of a standard mesh filter. So it really filters out the small stuff well, the big stuff not so well, but I don't care about the big stuff because it doesn't affect me as much.
What is the application of, is there there is a sheer wanting to know why these particles behave in a certain way, but I'm thinking the engineers here, how can they apply that to the things that they do?
Well, for engineering purposes, granular materials are different than solids, liquids, or gases.
Yeah.
A pile of gravel has a different behavior than a rock or a bucket of water. So, and it has properties that we've taken advantage of. I just saw one demo on the web when I was testing this out, where somebody took a jar full of rice and they stuck a rod into it. And stuck it in, wiggled it in the right way, and then literally picked up the whole jar with the rod, as if it was on a magnet. I was kind of surprised by that. I'd never seen that before. And I wanted to figure out how to do this. That's a very effective demonstration. Stick a rod in some rice and carry it with you. I don't know, there must have been something else involvement, because every time I've put something in rice and pulled it out, it comes out. Chopsticks and such. I don't think
it's like sand.
Well, sand can do that, but it flows more. So but there are unusual behaviors and unusual properties. If somebody's doing engineering work where they use granular materials, they certainly should know something about them. And they have other, like damping. For example, people want to, when soldiers want to create a bulletproof wall, they use sandbags because it's readily available, cheap, and does a really good job of stopping a bullet because the bullet hits one grain of sand, which is another grain of sand, which is another grain of sand. These force chains shift and change. Every time there's a collision, energy is dissipated, and a bag of sand can stop a bullet much more effectively than a sheet of metal. Not per unit mass or per thickness, obviously. 8 inches of steel will stop a bullet more effectively than 8 inches of sand, but for the cost and the availability, sand is very effective in doing things like stopping bullets. The the fellow I did the research with in Chile, Francisco Melhus, one of his projects is he's doing work for the Army, where he's trying to build a structure of grains that's effective at stopping impacts. And he's found that big particles and small particles in alternation, what happens is as the big particles move, the small particles rattle back and forth between the big ones, and every time they bounce around, there's dissipation. So a mixture of big and small particles can be very effective at taking energy and converting it to heat, dissipating it fairly harmlessly. That's one application. The mixing processes, all the things I discussed are some applications. Avalanche prediction, earthquake prediction, similar behaviors. I also know of a good talk when I was at a conference down in Chile where a fellow was looking on microgravity environments. He was looking at small asteroids, and small asteroids are basically piles of small rock and dust held together by their mutual gravitational interaction. The contact forces are so small because the gravity is so low that, like, if you kick up a dust cloud on one of these asteroids, it'll hang there for like 1 million years. And over 1 million years, it'll slowly collapse back to the surface of the asteroid. Some particles will fly off and go away because there's not enough force to keep them. But he was analyzing these small asteroids in microgravity environments with granular properties. So, not exactly an environment I've been to, but it's an interesting problem. So that's a few of the examples I can think of offhand.